So we know how to add vectors and subtract vectors. What other operations can we perform with vectors? Can we multiply vectors, for example? And the question becomes, what does it look like to multiply vectors? There's a few different things we could possibly do. For example, could we just multiply the x components and the y components, sort of like we add? And that's sort of what we do when we multiply vectors together. So for example, let's try that. Let's just multiply the x and the y components. So the x components would be 2 times 4, which would give us 8. And if we multiplied the y components for this example here, we would get 3 times negative 6, which would be negative 18. Well, it turns out these two numbers, if we were to represent these two numbers as a vector, it wouldn't really mean much to us mathematically. So what mathematicians have come up with, they actually realize that it's more useful if we add those two things together. The two products of the x components and the y components, we add those together. And in this case, it would be negative 10. So this process where we multiply the x components, multiply the y components, add them together, we actually call that the dot product of two vectors. And it's just one way to multiply vectors together, basically. We're going to learn another way to multiply them together called cross product in another lesson, but that is, that's a separate method for multiplying vectors. So notice actually, if we look at scalars, just regular numbers, we have four operations basically: plus, minus, multiplication, division. When it comes to vectors, so these are for scalars. For vectors, we have adding and subtracting still, but instead of multiplication, we basically have two versions of multiplication. We have one that's the dot product, and then one that's the cross product. It just looks like an X, sort of like multiplication does, but it's a different process altogether. So those are the sort of the four operations we can do with vectors. All right, so just looking back here at dot product, that's what it is. It's just multiply the x components, multiply the y components. So as we see here, essentially that's what this means. It's ax times bx plus ay times by, and that gives us the dot product of a and b. So we would say that that's a dot b, or in this example up here, we would say a dot b is just equal to negative 10. How do you think this applies to 3 dimensions? Well, in 3 dimensions, notice it's just going to be the exact same thing, except we're going to multiply the x components, we're going to multiply the y components, and we're going to multiply the z components together, and then we're going to add them all up. So c dot d is just equal to 2 times negative 2 plus negative 3, oops, plus sign, negative 3 times 1 plus 6 times 5. Which, if we add that all together, do that on a calculator, it comes up to 23. So the dot product of C and D is 23. Now that might seem weird. What does that 23, what does that number actually mean? It's just a number. And we'll get more into that on the next page and in future lessons. But just for now, realize when we dot two vectors together, our answer we get is just a number. It's just a scalar. So we don't actually get a vector out. It's just a scalar. So the question is, what does that number actually represent when we take a dot b? There's a few things that it represents, but for now, what we're going to talk about is this relationship here. A dot b actually has this relationship, which is sort of interesting, where if we take the magnitude of a and the magnitude of b, so the length of the a and the b vectors, and we multiply that by cos of theta, that's equal to a dot b, whatever that number was, which is sort of a weird relationship that occurs. But it does. I'm not going to prove it here, but if you're interested in proving it, you can just search that online. Cos theta, what cos theta means is the cosine of the angle between the two vectors. And this is useful because it actually can help us determine the angle between two vectors without doing a whole bunch of trig. And this is one of the most useful reasons for the dot product. So let's look at the example down here, right? It says determine the angle between these two vectors, a and b, the ones shown right here. So we need to do that. In order to do that, we can look at this relationship and see, basically we need each of the parts to plug in. So we need a dot b, we need the magnitude of a, the magnitude of b, and then we're going to solve for cos theta. So I'm just going to write that out, sort of that relationship. A dot b equals the magnitude of a, magnitude of b, cos theta. So we can start off by finding out what the dot product of A and B are. To do that, though, we need to know what A and B are, like the vectors, actually represent them as vectors. So vector A, if we write it in matrix form, looking up at that question up here, it goes to the right by 4 and up 6. So vector form would be 4, 6 for that vector. And vector B, if you look at that as well, it goes to the right 6 and then up 1. So it would be 6, 1, like that. So the first thing we need for this relationship is what A dot B are, or is. So A dot B, we now know what that means is just we multiply the x components of 4 times 6, and then we add that to the product of the y component, 6 times 1, and this just comes out to 30. So we know those that component there, or that part of that thing. Now we need the magnitude of the A vector and the B vector, and we know as well how to do that. So the magnitude of A, if we look back up here, the magnitude of A is just the length of the arrow, right? So we can use the Pythagorean theorem in order to find that. So going back down here, the magnitude of A is just going to be the square root of 4 squared plus 6 squared, which comes out to the square root of 52. And we do the same thing for the magnitude of B. It's just going to be the square root of 6 squared plus 1 squared, which is just going to be the square root of 37. Notice I don't really need to simplify these radicals yet because I'm just going to end up plugging them into the formula and multiplying them anyways. So now if we go back to this relationship, we can sort of just plug in each of the parts. So for example, A dot B is 30. The magnitude of A is root 52. The magnitude of B is root 37. And then we have cosine of theta. So if we just rearrange this for cos theta is going to be 30 over root 52 times root 37. And if you do inverse cos on your calculator and plug that all in one step without any rounding error, we're going to get theta in degrees as 46.8 degrees. There we go. That's the angle between those two vectors. If we look back at our question, does that make sense? The vectors are drawn to scale, and it does sort of look like it's around 45 degrees. So that makes sense that it's 46.8 degrees. That might seem like a bit of a process, but once you do it a few times, it gets pretty fast. Now, this is where it's really useful in this next example here. What about for 3D vectors? Try to picture those two vectors sort of floating out in space and trying to find the angle between those two vectors. That sounds like it's a very difficult thing to do. But the nice thing is that using that relationship for our dot product, it actually is the exact same thing as doing it for 2D vectors. So I'm just going to write out that relationship there. Oh, it's not A this time. Sorry, it's C and D. So C dot D would be equal to the magnitude of C times the magnitude of D times cos theta, which is the angle between them. So again, if we just find these things, if we find C dot D, the magnitude of C and the magnitude of D, we can find the angle between them, which is pretty cool. So starting off with C dot D, I'm just going to do this work off to the side. If you want, you can plug it directly into that relationship there, but I just like to keep that nice and clean. So C dot D is just going to be 2 times negative 2 plus negative 3 times 1, it's a negative 3, times 6 times 5, plus, my bad, I'm going to erase that, running out of space here, that's why I'm writing very small, plus 6 times 5, and if we do that calculation, we should get C dot D, those negatives, take away, so we end up with 23 as C dot D. We can also find the magnitude of C just by using our 3D Pythagorean theorem. It's just going to be the square root of 2 squared plus 3 squared plus 6 squared. Again, I'm ignoring the negative sign of the 3 because we're just finding the magnitude here, and negative 3 squared is just 3 anyways. So the magnitude of c is going to come out to root of 49, which we can just write that as 7. And then the magnitude of d, same idea, 2 squared plus 1 squared plus 5 squared, and take the square root of that. So the magnitude of d ends up being the root of 30. We plug that all those nice things that we just found, into that formula. 23 equals 7 root 30 cos theta. If we rearrange and solve for theta, we end up with an answer of theta equals 53.1 degrees. There we go. Think about what we just did. We found the angle between two three-dimensional vectors, which sounds like it's a very, very difficult problem. It would be if you're looking at the image and trying to sort of figure it out algebraically in some other way. But using dot product, we can very easily find that angle. One other thing I want to point out about this, when we're finding the angle between two vectors, that cos theta and that theta, what that theta represents is it represents the angle of those two vectors, between those two vectors, if you place them both at the origin, or tail to tail. So the end of the vectors, see the non-arrowed ends of the vectors, if you put them together, what would the angle be? That's the angle we're finding. Not the same angle as if we were adding them together. It's as if they were tail to tail. So in this next example, we're given three sets of vectors, three pairs of vectors, and we're asked to determine what A dot B would be for these three sets of vectors. So again, if we use that relationship, we'll start with the first one here, of A dot B is equal to the magnitude of A, magnitude of B, cos theta. We can just think about what we can plug in there. Well, we can just plug in those three things, no problem. The magnitude of A, it tells us is 3. The magnitude of B, it tells us is 2. And theta, it says, is 50 degrees. So we can figure out, 50 degrees. We can figure out what A dot B would be. 50, I'm having problems with this question. 50 degrees. We can find out what A dot B would be if those things were true. And we can just simply plug that into a calculator, 3 times 2 times cos 50. And that gives us an answer of 3.86. So that's simply what A dot B is for this question. We can use this to answer other types of questions where, for example, we would need to find one of the components of the vector or something like that. But that's what it is, it's 3.86. So try the other two problems yourself, and then I will put the solutions up. So here's the answers to question 3. Again, our answer to the first one was A dot B was 3.86. Our answer to B was, or the second part was negative 17.5, and the answer to the third one was 0. Now think about those three answers. 3.86, negative 17.5, and 0. What would cause that first one to be positive, that second one to be negative, and that third one to be 0? Well, A and B are just the magnitude of A and the magnitude of B are just magnitudes, so they're both going to be positive. So really what determines if it's positive or negative is going to be the cosine. When is cosine positive, when is cosine negative, and when is cosine 0? Well, if you think about it, cosine is positive when x is less than 90 degrees. So whenever the angle between the two vectors is acute, we are going to have a positive dot product. Whenever the angle is greater than 90 degrees, we know the cosine of an angle greater than 90 degrees is going to be negative, right? Because you're in that second quadrant there, if you're thinking about your unit circle. So when it's obtuse, you're going to have a negative dot product. And lastly, what happens when it's exactly 90 degrees? Well, the cosine of 90 degrees is 0. So when you have a right angle between those vectors, we have 0 as the dot product. So this is useful because we can tell right away by looking just at the sign of the dot product whether two vectors are acute, obtuse, or at 90 degrees to each other. And that answers our last question down here, which is what will be the dot product for vectors that are perpendicular? Where perpendicular is another way of saying at right angles to each other. So basically, if the vectors are perpendicular, if A and B are perpendicular, then A dot B is going to be 0, because cosine of 90 degrees is 0. So this is a very quick check, a very useful quick check to check if two vectors are perpendicular to each other. Lastly, at the bottom of the page here are two properties of the dot, or a few properties of the dot product. Some of these might seem obvious, but we just have to highlight them so if they come up, you know how to use them. So down here, let's actually zoom in on some of those. So the first products of the dot product are that A dot B is equal to B dot A. Basically, it doesn't matter which order you take the dot product in, which vector you put first and second, you'll get the same dot product out in the end. And that makes sense if you just think about what's happening. You're just multiplying the components and then adding them together, so it doesn't matter. Sort of like just regular multiplication for numbers, doesn't matter the order. Same thing with the second property, right? For the second property, A dot B plus C, if you add the vectors B and C together, it's the same thing as sort of distributing that A to each vector. Which one do you think is easier to do? That first one over here or the second one over here? Well, it probably depends on the question, but a lot of the time I think it's going to be easier to do this first one, just add those two vectors together and then take the dot product, as opposed to taking two separate dot products. So this is just a little trick that we can use to save some time. If we then go over to these last two, this one's a little bit more interesting, that A dot A. So if we multiply a vector, or if we take the dot product of a vector in itself, the answer is just going to be that vector squared. For regular multiplication, this makes sense. If you multiply a number by itself, it's just going to equal that number squared. But maybe it's not so obvious with vectors. It does, however, come out to the magnitude of A squared in this case. And lastly, if we multiply a scalar, k, by a vector, and then we dot that with another vector, it doesn't matter where we multiply by that scalar. We can multiply just b by that scalar, or we can take the dot product first and then multiply them both by that scalar. So these properties will help you answer problems that you encounter.